this is more still philosophical, and to me, when I discovered this more than 40 years ago, it was very startling, and it changed how I looked at the world so much that I didn't want to talk about it because it was out of the ordinary. And there's the spooky action at a distance. So why am I bringing up the double slit experiment? You have an electron gun shooting slow electrons into a screen with two slits, and on the other side of the screen of the slits, there's a screen that detects the electrons, and instead of having little marbles going through, it's waves, and they interfere with each other. But if you put a magnetic field near the electron gun, they're little marbles again. But I won't go into that. You can channel Richard Feynman to talk about that. So the question is, does the electron exist between the gun and the screen? And what I'm saying is the electron does not exist. The probability of detecting it exists. And as soon as the probability is high enough at a detector, an electron will appear and the entire wave will collapse instantaneously across the entire universe, no matter where it is. So no energy is transported in the wave. That was very, very nice for me. I just did not like something like energy being transported very fast. But something like probability, I don't mind probability collapsing. So I'm saying the electron does not exist. It's turned into a wave as soon as it gets out of the electron gun. And then there's a joke that physicists have. How do you trap a lion in a desert? Well, the Schrödinger method, the lion has a wave function. There's a positive probability that there's a lion in the cage. Just sit down and wait. And as soon as the lion's in the cage, you close the cage. In the Heisenberg method, you disturb the lion when you observe it before capturing, so keep your eyes closed. And physicists find that funny. So what happens when you see a star? You only detect discrete point particle photons, generally by the photoelectric effect, or what the photons do to the rods and cones in your eye. Before that, I'm saying there are no photons. No photons are coming out of the star. There's only probability coming out of the star that you detect. Only when the probability is high enough, you will detect the energy associated with that waveform, which is not the philosophy that most people are taught in college. So what is in transit? Are there light waves, electromagnetic waves in transit between the distant star and the detector, your eye? Is the energy spread on a spherical wavefront that collapses via spooky action at a distance? Any light years away? No, that's not right. Are photons in transit? No, that's not right. What do we really see when we see something? And we all here are considering ourselves sane. And sanity means we agree on what our brains are interpreting of the photons entering the eye and the sound wave, the phonons activating your eardrums. But we're not seeing the screen, we're seeing the probability of the photons appearing at your eye from the screen. You're seeing the probability of the photons coming off me in your eye. There are no electromagnetic waves, which is startling to me. That's my interpretation. And only in the classical limit will it be interpreted as electromagnetic waves all the time. So Howard's at the bottom. No electromagnetic waves except as the detected effects of the waves in the classical limit. So when you send radio waves through an antenna, you can treat the radio waves as waves and not as photons. And there's so many photons that you might as well call them waves, and you won't be wrong. So what if there's only one star? And that's, I cut and paste an eye. The star is so far away that only when the probability is high enough for a photon to appear in the eye will you see a photon, or will you see a star. And if it's far enough away, there might be fluctuations from that star. So there might be twinkling even in outer space. Now, since I've never been in outer space, and they tell me that there is no twinkling, I'll have to accept that. But according to this, if the wave function is weak enough and the probability goes up and down, the star might twinkle. Now you realize that the eye, let's say, is two-tenths of an inch. I'm going to use that. And Palomar telescope is 200 inches. So you have an aperture of 1,000 times larger. What's 1,000,000 times the area. And if you have to have the telescope on for 6 hours to see a star, that's 6 million hours of watching to see a photon, see enough photons for photographic plate. You'll never see them in your lifetime. And the sky will be dark, but through a big telescope you'll see stars. But what if there are more stars? Many stars. The probabilities are called disjoint. The disjoint probabilities mean they don't all gang together and make a bright sky. If it's going to take 6 million hours to see one star, it's going to be 6 million hours to see any other star. And occasionally there might be a little flash by accident or probability going up. And some stars can twinkle. So if the probability is high enough, a photon will appear at the eye with the passing of time for each star independently. So what I'm saying is there are no electromagnetic waves, just probability. So then I thought, there's no difference between light from a star and light from a fluorescent bulb. So I'm saying that everywhere there's just probability of light. There's no light. And how do we test this? If there's a twinkling star having two telescopes with different apertures and measured outputs, if the twinkling star doesn't twinkle at the same rate in one of the telescopes, or doesn't twinkle at all with a smaller in the larger aperture, this might be a verification of what I'm saying. But what I'm saying is this theory, if you want to call it that, covers all the bases, and I've now presented it to several physicists who I think are pretty high powered. And maybe they're being nice to me and saying, no, you're crazy, but that's no news to me, I am crazy. So one could set up an experiment to see if this theory is correct. So it's real science, it's disprovable. But there are implications here.
Jack?
Yes.
So how do you, my observation is that planets don't twinkle.
That's correct.
Okay. How does that fit into...
there are more photons. The electromagnetic density is higher. The probability is higher. But many stars don't twinkle. Only a few stars twinkle. And one explanation is there's a bigger disk. But if it's atmospheric, then the Palomar telescope, which is in the atmosphere, would have blurry images all the time. It doesn't. It has pretty sharp pinpoint pictures. And so the explanation of a twinkling star being done by atmospherics, to me, does not sound right. Because if it's why longitudinally, why not azimuthally? Why not blur everything in all directions? Whereas through a good telescope, you see point stars. So is this right? Is it wrong? I don't know. So I'm thinking about more and more what happens at the end of the universe. Being almost a cosmologist, knowing nothing about it, I can do this. When everything has decayed, even the protons, and there's nothing but probability, and there are no detectors, what's the temperature? Well, if an open system goes all the way to the end, the entropy should be maximum. But it can't be if the temperature is 0. So what happens at the end of the universe when there's nothing but probability occurring? And then it gets a little weird because I thought of a geometry that it's a multidimensional geometry, such that every straight line in the geometry has 2 points at infinity, and they're the same 2 points for every line. And you could gin up a geometry like this. So that eventually all the rays, all the neutrinos, all the photons, all the probability gangs up at these little points. And then I won't say anything more. And I'll leave this with you, and you've all been very silent. And silent means assent, maybe.
Means confusion.
And thank you for listening.